This video tutorial presents a generic experimental procedure. Please consult your class notes for term-specific instructions. In Part 1, a sinusoidal voltage signal caused the speaker diaphragm to move up and down, moving air and, in some cases, generating an audible sound. In Part 2, the system is reversed. The speaker is oscillated or shaken up and down, which generates an output voltage at the terminals. This is similar to a motor and a generator. If voltage is applied to an electrical motor, the shaft rotates. In the reverse system, the motor becomes a generator. As the shaft is rotated, a voltage is generated across the terminals. The lab setup for this experiment consists of a function generator, a power amplifier, a resistor bank, a loudspeaker and accelerometer mounted to an electrodynamic shaker, and several metal washers to use as the loading masts. This block diagram provides a simplified view of the system. LabVIEW controls the Keysight function generator, which outputs a sinusoidal signal to the power amplifier. The boosted signal drives the electrodynamic shaker, which excites the loudspeaker and outputs a voltage signal denoted as V1 across a variable load resistor. Since the impedance of the load resistor is known, the output power may be calculated by implementing Ohm's law. An accelerometer provides a reference signal of the driving dynamic motion throughout the test. Here's a more detailed diagram of the wiring. This diagram is included in the student guide. First, the actual impedance of the load bank needs to be measured. The load bank has 4 resistors with nominal values of 1, 2, 4, and 8 ohms, which can be toggled into the circuit using a selector switch. The various switch combinations enable the load impedance to be set from 1 to 15 ohms. To measure the actual impedance, connect the load bank to a digital multimeter and set to measure resistance in ohms. Progressively increment through all the load settings and record the measured impedance. On your desktop, open the X95 shortcut folder and select Energy Harvester Main shortcut. LabVIEW will take a few minutes to load. Once the LabVIEW program is open, activate the Configure tab. Navigate to the function generator port and use the pull-down to select the valid USB port to connect with the Keysight function generator. Next, verify the amplitude voltage is set to 0.1 volt and magnitude scale is set to linear. The accelerometer offset needs to be determined to compensate for Earth's gravity. When properly set, the sensor output should be around 0 volts when motionless. Turn off the power amplifier. In LabVIEW, select the Configure tab. Navigate to the channel definition for the ADXL335 accelerometer and set the offset to 0. Now select the Snapshot tab at the top. Uncheck the load resistance voltage in the plot legend and click the green Take Data button. After the defined test duration, a plot of the accelerometer output is displayed. Use the cursor to estimate the average value. Alternatively, the data can be saved and analyzed in MATLAB to determine the average value. Return to the Configure tab and enter the estimated value of the accelerometer offset, but with the opposite sign. To verify the setting, return to the Snapshot panel and rerun the test. The average output should be around 0. When finished, click the Frequency Sweep tab to return to the main panel. Reconnect the load bank to the output leads from the speaker. Turn on the Keysight function generator using the front button. The boot up sequence takes about a minute. Turn on the power amplifier using the front button. Start with the orange stage unloaded, i.e. no washers, on the speaker. Set the load resistance to 1 ohm. First, perform a coarse frequency sweep to find the resonant frequency. Set the range from 10 to 100 Hz with a step size of 5 Hz. We'll use the default settings with a delay of 2000 milliseconds between tests to ensure steady-state conditions, and set the repetitions to 1, i.e. no repetitions. Press the Take Data button to start the sweep. The various signals are plotted in LabVIEW along with the construction of the Bode plots as the frequency is sequentially incremented over the defined range. The frequency sweep will take several minutes to run, so be patient. Use your results to identify a narrow band around the resonant frequency. In this example, the peak is between 60 and 70 Hz. Rerun the frequency sweep over the refined range using a small step size for improved resolution. When finished, save the data to your desktop using a descriptive file name. Using this narrow frequency range, repeat the test with progressively increasing impedance up to 15 ohms. Save the data after each run. After sequencing through all the required impedance settings, increase the diaphragm's mass by adding metal washers to the orange stage, up to 5 washers. Snug the wing nut to prevent rattling. Do not exceed 5 washers. Reset the load bank to a load impedance of 1 or 2 ohms. Since the mass has changed, we need to perform a coarse sweep from 10 to 100 Hz with a step size of 5 to find the new resonant frequency. As before, use the results to define a narrow frequency range for the system and set the step size to 1. Proceed to test with other load impedance settings and save your data for each run. This flowchart provides an illustrated view of the general procedure for this lab. This flowchart is included with the student guide. Be sure to save your data before leaving the lab today.